Well, as Becky said, my name's Sarah, and I'm going to talk to you about predictive maintenance, hopefully demystifying it for you and making it easy to understand. But before we jump into that, my name's Sarah. I run one of the biggest tech meetups in Boise, Idaho. I also help out with the Idaho Technology Council, and I run a podcast called Sarah in Tech, where I interview all my friends and ask them how they got into the roles that they got. Some of them are directors or CEOs and what sort of career moves they made to get there. And I've had a lot of fun and a lot of self-exploration in this process. So what is predictive maintenance? It is the idea that we can predict when something is going to break before it breaks and affects the normal workflow. So right now, what goes on a lot in this space is that every week, every month, or every year, someone goes out and checks a belt, a chain, a brake in a piece of equipment and wastes a lot of time checking to make sure that that piece is behaving in the way that it's supposed to. And I'm going to talk about a hypothetical person named Bob and how he deals with having to constantly go out and check things. And the idea is that we will eventually get to the point and say that this item is going to break. Before it breaks, Bob goes out and sees that the brakes on a roller coaster, if you will, are about to give out and replaces them while the roller coaster is down at 2 a.m. and no one's trying to ride the roller coaster. And then no one is affected by the brakes going out on the roller coaster. So what do we need to do to get to the point that the roller coaster, the nuclear power plant, or a server doesn't have these downtime events happening? Well, we need data. We need a team of individuals. It's not just me going in, being all rough and tough and putting those machine learning and data science models into place. It's a whole host of individuals. And then I'm going to go through the use cases that I've actually worked on, which is nuclear power plants, high performance clusters, which is just a fancy way to say servers, and roller coasters. So what type of data comes into this space that we're able, such as Bob, to say that, hey, the brakes are going to give out? And the type of data that comes in is kind of boring. It's like binary data, on, off. And the frequency of it dramatically changes depending on what you're in. Sometimes it's every millisecond, every second, or every single minute. And using binary data, which sounds really boring, you're able to actually do really complex things. And that's one of the ones I'm going to do a deep dive on and talk about duty cycles, and even have a little GIF that shows how it works. There's analog data, which is just a way to say that there's whole numbers and we can measure them every time unit. Vibration monitors, which look at how much movement happens on something, and infrared thermal scans, so we can see how hot pieces of equipment are getting. And usually the hotter a piece of equipment is, the more likely it's going to break very soon. There is text, and so someone writing down, hey, I think this is going to break soon, or hey, this actually broke. And then you have handwritten notes, and how do you transfer that handwritten notes into something standard? And that's just a fun process in and of itself. Or actual photos or videos of operations happening in these spaces. And we can use those to say whether or not something's going to break soon. So like any data scientist, data engineering, the way that you take that data from those raw files, that video or that binary data, and actually put it into a database is insanely important. So we have all of these sensors, whether it's a camera, vibration, a thermal scan, coming in to the database, and we try to aggregate it and make it easier to understand via the use of frequency tables, latency, which is like measuring the time between one sensor and another sensor, and also clustering. So putting sensors that behave similarly to one another together, and many more aggregations that I'm not going to get into right now. But all of that, if you remember from like high school and algebra and stuff, we have y equals mx plus b. So those are our inputs or our x variables. And then the output, which is awful and sometimes very difficult to distill down, is those handwritten notes from the maintenance department, and trying to go through that process of standardizing it. And that's your y, or your output. And through that whole process of all the sensors and those output text, we can build these predictive maintenance models. Okay, so here is a flowchart explaining how the sensor data, the event data, and how we refine these machine learning algorithms even further. So the sensor data is kind of it is the blue space, and that's the first step you need to get this done, is an actual feed of information coming off of the object, device, or what have you. And you have to distill it down to meaningful measurements in order to understand what's going on in the space. So without the sensor data and out a lot of historical data of the sensor data, you can't get predictive maintenance up and going. And the next space is the event data. So those handwritten maintenance notes, and standardizing them to what we call a ground truth, in that we take those event data and sometimes they say really interesting stuff, but it's not actually relevant for what's going on. So someone says, hey, I went out to the server and I touched it and it was hot, but they forgot to say what server they went out to. And saying it's hot is relative to each individual. And as a data scientist, you want the server was over 120 degrees and it was this time of day and this is the server name. And without that amount of detail in the notes, the maintenance notes tend to be not very useful. The thing that we do is we combined the blue area and the yellow area, and we make the green area. So that's where all the fun data science machine learning happens. We take the sensor data and we put it with our ground truth, and together we start building out the predictive maintenance algorithms. And a lot of time it's working with the subject matter experts to see what's going on in that space and what they think. Most of the individuals have been working in the space over 30 years, and there's no way a data scientist with only about a decade of experience is going to be able to come in and build a model better than what their gut instinct is from working on the equipment over 30 years. And so iterating with them to a point that we can get the machine learning to a good place is one of the most important things. There are a lot of host of additional machine learning refinement that you can do, which is the purple space, to help make the output better. Of course, everyone needs to see a visualization, not just say, well, the mystical, magical AI said something was broken and we should probably fix it, but showing graphics that explain why we think that is always very important. And so that's kind of the blue and the green area, or excuse me, the purple and the green area. So who exactly is needed to build this predictive maintenance algorithm? So the team is not just a data scientist. It includes a data engineer, the subject matter expert or SME, a visualization expert, and a line of business user. So all of those individuals constantly work together on the product to make it useful. They work through the analytical layers and making sure that we're using the correct tool set for the customer that we're at, and also making sure all of the data feeds are coming in and being processed correctly, and putting that into a database, and finally putting that onto an on-cloud or in-prem solution for the customer, so we can react in near real time, and the maintenance can happen in the natural downtime of the differing pieces of equipment. So let's actually talk about the use cases. Nuclear power plants. So preventative maintenance is performed very regularly in nuclear power plants. When it happens in a nuclear power plant, the whole plant is taken down for several months at a time. This is really problematic, as nuclear power plants are usually the load-bearing power plant, meaning that they provide most of the energy to the grid that they're on. And so downtimes really negatively impact everyone. So we want to reduce the downtime as much as possible. But usually they're taken down for 3 months at a time. And as they do more maintenance, so Bob going out and checking that chain or that lever or that brake every single month. In addition to that, at a nuclear power plant, it's usually a lot of analog devices that are checked and then noted down what the measurements are. But as they start going through the preventative maintenance, that 3-month window starts becoming longer and longer. And that's just a really bad thing for everyone. So what we do in nuclear power plants is we look for trends in the maintenance to indicate that there is going to be a system-wide failure. I know that's kind of scary to say at a nuclear power plant, but I want to emphasize that every single nuclear power plant has a backup. Every backup also has a backup. And so there's an A plan, a B plan, and a C plan, on top of the fact that there are mountains of manuals on how to correctly address every single situation. And so nuclear power plants are insanely safe. I worked on the human factors, the probability space of the likelihood humans will fail in a nuclear power plant, and want to emphasize it's very safe. But the way that we dealt with doing predictive maintenance or looking at maintenance in nuclear power plants is we used compound distributions in generalized linear models. Those compound distributions were a lot of really fun, difficult math in the space. So that way we could correctly identify what type of trends were happening. One of the papers I worked on was fitting of failure rate data to gamma Poisson distributions, utilizing the method of moments, which is just a mouthful. But there are other things that happen in nuclear power plants that we don't really think of that affect the many different systems there. And the next type of use case I'm going to talk about is compute clusters, or servers, if you will. And clusters and servers are very different from a lot of other predictive maintenance use case scenarios, because preventative maintenance, Bob going out and checking the brakes, the chain monitors, or the switches, does not happen. In servers, the software is updated intermittently. It isn't rolled out across all of the servers all at once, especially in a server farm, if you will. And the IT department only reacts to downtimes. So if they see an imminent failure, they're not going to take actions necessarily, because by that point, it's just too far gone. And the lack of reaction impacts job execution and scheduling. What the ideal situation is they get a notification saying, hey, this job is going to imminently fail. We can see that this job takes several months to compute, and someone should shut it down gracefully so that way it's in a place where it can be booted back up on a different set of servers and continue running and calculating what it needs to in the space. Servers farms are very difficult to deal with because they have a lot of different monitoring systems. And so it's very hard to get a one-to-one. Sometimes even the timestamps between the servers aren't all aligned, and it's very bothersome to find groups of servers in the same cluster working together because of the timestamping differences that just exist. And overall, obviously, downtimes are really, really bad. Scientists don't like it because they have to restart long-running jobs. They could lose months of work, and it increases everyone's cost. Some data sources, just like off the top of my head, is the system log or failed job reports or any other number of loggings in the space. But getting those to all line up because of the disparate data sources is very difficult. And so, but usually in the space, there's well over 9 different data sources that all need to be attempted to line up for just one server. And as you can see with the little sample that I have on the screen, there are many, many messages that are happening in the same second. So just for at the mark for 39 seconds, you get multiple messages. And this is just a normal running job and not necessarily a failure event. And so because of that, it's a lot of effort to standardize and mine for metrics, looking at CP usage or temperature or other things in the space. And vector embedding is just a fancy way to say, we did natural language processing. So we took all the different words that were in these servers, like merge slow at this timestamp, and turned the words merge and slow into numeric values that we could actually analyze to get an outcome. And there were a lot of different metrics that we can use to perceive those failures and say, hey, this server is going to fail imminently. And we have like ARIMA models, native Bayes classifiers, random forest autoencoder, neural nets, and natural language processing in that space to help us get to the point where we can say, hey, this server is going to go down. We know it's going to go down within the next hour. You should probably start shutting down those jobs before they hit the end time. Now, what does that actually look on our end? Because we know that there are certain words that we see a lot of that precede a failure. And so if we look at the black bar chart, we see that the shape of the black bars, each bar is representing the frequency of a different word, is different sizes. And so the black is just all of the logs for a server. If we go into the red bar chart, we see that the shape of the red bars is very different. And so the word frequency in failure logs or failure servers is very different than the black. And then the green is just logs for jobs that succeeded. And that shape, again, is dramatically different from the red. And if we put the black, or if we put the red and the green together, we would get the black, which is a combination of both failure and non-failure. But there is a correlation between the failure of a job and the top words that we see in those log lines. The problem that runs into it is each server's software in that space is different. And because the software is different, the language that we can use to identify that that server is going to go down is, of course, different. And so this isn't a very consistent method to say, hey, server ABC is going to go down soon. And so the idea is that an algorithm goes in and reads, say, 100 lines of what's going on in the server. And within the first 100 lines of a job, decide what's the likelihood that that job is going to fail on those servers. And if it's highly likely, then that job needs to be shut down. And another job that's more suitable for the servers would be run on that instead. And that way more work gets done and everyone's a lot more productive. And so we can get that likelihood of failure using metrics, which is numeric values of what's going on, and changing the words into values using natural language processing. So we can target the predictions of what's going to happen in the space, but without regular measurements like CPU usage or temperature or others, then we have to rely on natural language processing in the space, and it's not always very effective. So I see Janice saying that our failure is hardware or software or both. And in this space with the servers that I was working with, it's almost all software failures. Hardware failures was like less than 1% of what's going on. And it's just, they didn't have a very good methodology for doing software updates. And they were very averse to putting actual metrics, so CPU usage and temperature directly embedded in the logs. And they weren't giving me access to that. So due to that, it's just a very difficult space to work in. And then finally, one of my favorite predictive maintenance use cases is roller coasters. So preventative maintenance is regularly performed on preventative maintenance. So Bob going out and checking the brake or a switch or a chain monitor is regularly performed on roller coasters. There are daily, weekly, and monthly schedules that they adhere to in order to get good results. Each roller coaster is unique and takes years of training before they'll just let you go out and perform maintenance on it. So I don't want you to think that individuals that have roller coasters don't take very good care of those roller coasters. And a lot of those roller coasters, while they've been around for 30 plus years, there are parts on it that have never been replaced, but that's because someone goes out very regularly and checks to make sure that those parts are still good. And there are other parts of it that are replaced almost weekly. And that's why they have these different schemes of daily, weekly, and monthly maintenance. The reason you don't want a roller coaster go down is because not only does it suck being the one at the park who can't go on the roller coaster, it also affects the bottom line of a park. So if a roller coaster is almost consistently down, and that's the reason that you went to that park, or there's a group of coasters that are consistently down, chances are you probably won't try to go back to that park. So a lot of what goes on in a roller coaster is they have programmable logic control, a PLC, that's tapped to create a data stream for each coaster. And what we try to do is identify abnormal behavior. So excessive brake usage, and you can see the temperatures getting way too high, or the chain monitor is saying the chain's running way too much or way too little. And what we're trying to see is this is what your normal run and operate is, and this is abnormal, and someone should probably go check up on it. And then this over here is also abnormal, and you should probably go check up on it. And there are a lot of really fancy data science words like modified ARIMA models, hyperparameterization, lots of goodness of fit, and even some neural nets, which are considered to be artificial intelligence. But using all these tools to say, hey, the roller coaster is probably going to break within the next week or two. Someone should probably fix it tonight at 1 a.m. or 2 a.m. when everyone's off of it. And so that way it doesn't go down anymore. And there is no standardized maintenance log. So no one's writing, hey, X part of coaster broke today. And that's one of the things that makes the space difficult to work in, because it's this thing called unsupervised, meaning that all we have are the sensors on the roller coaster to say what's going on. And we don't have the output or the Y variable. Okay, so what does a signal off of a roller coaster actually look like, Sarah? So this is a hypothetical sensor on a roller coaster that I synthetically created so that way you can see what it looks like. And while I know that the pink section is moving very slowly, this would actually be occurring in milliseconds. And so you can kind of get a feel for the amount of information that would be coming in as a data scientist, and you have to distill this down to meaningful values. It's very difficult, but the general idea is that you can yes, that's right. It is no fun being the one caught on a roller coaster when it sticks. This hopefully prevents that. So the idea is that you take the different parts of the commands. So this is what we call a duty cycle. And on a roller coaster, you only see zeros and ones a lot of the time. So even on those chain monitor, yes, there's a chain monitor. No, there's a chain. There isn't a chain here right now. And as a sensor goes past the chain, it says chain, no chain, chain, no chain. And we will see ones and zeros in that space. Now, this is what we're looking at is a signal for a cart on a roller coaster to go to another part of the roller coaster. And so a break, which is there is no signal being sent. And then all of a sudden the signal being set is noise. So it has no real meaning or value, and no logic knows what to do with the cart. It's very common for signals at the beginning to be cut off. And then after that, you can see that the signal goes down and up with the zeros and the ones, and the zeros being very short and the ones having a very specific length of 200 being sent. And so saying this in ones and zeros, like a Morse code almost, gives us the cart the signal to go to the next part of the track. The idea is that we'll look at the frequency of brakes or noise or go signals, so the command, and we see how often it happens. Again, this is synthetic data, but this is very similar to what you would see on an actual roller coaster. And you can see how much it varies. So this is quite a few days of data. And at the very beginning, someone in maintenance goes out and runs the coaster through the ride to make sure everything's okay. And that happens for the first hour or two of each day. And then it goes up to its normal run and operate. And so this is the frequency that we see a go signal every hour. So this command line of 40, 20, 40, 20, 40, 20, we see this frequency every hour. And we have to define when it's abnormal. When is this part of the track saying that, hey, I told the cart to go too many times, and now I'm probably actually broken and I need someone to go out and perform maintenance on me. And unfortunately, we can see in this bit of information that there is no abnormal event happening. And we can see in the middle, right by February 21st, that there is no, the next day, the whole attraction was taken down and they were able to perform maintenance during that. But this is just one sensor off of a roller coaster, such as A, B, C, D. And each roller coaster has thousands of sensors, and each sensor has multiple signals: go, brake, noise, and other things. And so that's what one sensor breaks down to, all of these different graphs. And how do we take this binary sensor that's saying 0, 1, 0, 1 and turn it into all these different signals that's meaningful? So what we ended up using was an autoencoder to identify abnormal behavior to see what's going on. An autoencoder is normally used for compressing images, but it also works with identifying abnormal signals being sent on the roller coaster. Anyway.
Hey, Sarah. Yeah. Hey, Sarah, thank you so much. We're running short of time.
Okay.
So we do have to roll on, but thank you so much for sharing your expertise with us. That really made me think. So thank you for that. I just thought of a lot of different kinds of scenarios as you were speaking. So thank you so much for that.